So last time, I promised you I would tell you what those funny piecewise linear pictures that I've been drawing and calling tropical plane curves, what they actually have to do with algebraic curves. And there are many ways to see that and to talk about this tropical degeneration, you could say. And a way that I particularly like, because I find it rather simple, intuitive, and concrete, so I think it's very suitable for this school, is to just work over a field with a non-Archimedean valuation. And to be really super precise, I'll fix my field to be the field of Puiseux series. So let me say over C. For simplicity, it could also be over some other field. And you write it with such double brackets in T. And what it contains are, well, formal series, of course. C1 T to the A1 plus C2 T to the A2 plus and so on. And the coefficients are supposed to be non-zero complex numbers. And then this is maybe a bit unusual if you compare to usual power series. The exponents, they are allowed to be rational numbers, but they need to share a common denominator. And you need that to make multiplication well defined on this field. So we consider this field of Puiseux series, and at first glance it seems to be a bit of a weird field, but it turns out it's an algebraically closed field, and we know very well that as long as we work over an algebraically closed field, we're pretty much safe in algebraic geometry and things work out the way they should work out. So we can, just use this field and not worry about it. Yeah, we can't draw pictures, but we can't seriously draw pictures over C either. So that's fine. Okay. What is good about this field is that it comes with a non-Archimedean valuation. So there's this map Y, which goes from K to R union infinity, and it sends 0 to infinity, and then a formal series of this form C of t, like above, to the least exponent, A1, I called it in this notation, above. So, and that thing defines a non-Archimedean valuation. What does it mean to be a non-Archimedean valuation? It means the valuation of a number is infinity if and only if the number is 0. That's true for us. The valuation of the product of two numbers is the sum of the valuations. Yeah, that's also true for us, because if we multiply two series, then the least exponents will just add up, right? And finally, the valuation of a sum is bigger or equal to the minimum of val A and val B. Yeah, and this has to hold for all A, B in K star to make this a non-Archimedean valuation. And also this last axiom for our valuation on the Puiseux series is clearly satisfied, because if we add two series, then where's the least exponent going to be? Well, generically, it's just going to be the least of the smaller one, so to say, right? The smallest least exponent of those two. But of course, it might happen that one series starts with, let's say, t plus whatever, 2t squared, and so on. And the other starts with minus t plus 3 to the 5/3 or so, yeah? And then the leading terms just cancel each other out. And then you don't really know what you get, but something bigger, right? So it doesn't have to be equal to the minimum. But the minimum, what it does, it mimics the generic behavior. Yeah? So if you pick your series at random, then you won't have this special cancellation behavior. Then this will be the generic behavior. And of course, you look at these operations and you all recognize them, right? These are tropical operations. Plus and min, okay, I used max. But to get to max, I just have to use minus val when I tropicalize, when I degenerate. And you know, this minus sign death, you have to die this way or the other. You can't help it. It's just there. Okay. So as I said, this field is algebraically closed, and we can very well just do algebraic geometry over this field. In particular, we can study plane curves, algebraic plane curves over this field. So I just take a polynomial over the field of Puiseux series, multi-index notation I want to use here. And then the theorem, I wanted to give a name, sorry. It's this theorem, Kapranov's theorem. Kapranov, okay. And then what I do is I have the vanishing locus of this polynomial. I only care about the torus points, so points in k star to the n, so x is my shorthand notation for multi-index x1 up to xn at the moment. Actually, you can just think n equal 2 if we want to focus on plane curves, right? N equal 2 maybe. Anyway, so we look at torus points of our algebraic hypersurface in general, or algebraic curve if n is 2. And then what do we do to the points in there? We just apply for x in, we just apply minus val coordinate wise. Minus val x1 up to minus val xn. Okay, then we get a tuple of points, which is in q to the n actually, because the the exponents of my Puiseux series are going to be rational numbers. So we get a bunch of tuples in q to the n. Yeah. We take the closure in the Euclidean topology of R to the n. Yeah. And then the statement is that this thing is the tropical hypersurface defined by the tropicalization of the polynomial f. Now, I think I still need to tell you what the tropicalization of a polynomial is. What is it? I need to tell you what f is. Let's invent some notation. F sum over some multi-indices alpha, a alpha, x to the alpha. And then trop f, what do we do? Well, obviously, we should replace all operations by tropical operations, right? And then we don't quite like the Puiseux series. What do? Well, we do minus val to it. Then we are in our tropical semi-field, right? So trop f is going to be the maximum of over all alpha of minus val a alpha plus, alpha times w. Let me use w as the variable in the tropical world for the moment. Okay, so here's a tropical polynomial. These are the things we looked at last time, right? We know how to produce a tropical hypersurface for those tropical polynomials. These are the pictures we have been drawing last time. And now I claim that those pictures are actually images of algebraic plane curves under this coordinate-wise valuation map. Yeah? And that's a bit of a miracle, I have to say. When I learned about it at the first time, I was pretty surprised. Because, you know, algebraic curve over this funny field of Puiseux series, that's a crazy object to begin with. Then you apply this minus val, which is a very brutal map somehow, right? And you see something interesting. Who would have expected that? Yeah? But that is actually the miracle. And that is what tells you that those funny objects we're drawing when we are in the purely tropical world, they're actually coming from algebraic curves, or at least they have a chance to come from algebraic curves. And this also explains why they behave in the way we expect them to behave. Yeah? Why two lines intersect in a point generically, why there's one line through 2 points, why Bezout's theorem holds in tropical world. There's some justification, philosophical justification for this, at least after we learn that tropical curves come from algebraic plane curves, right?
What's W?
Sorry?
What is W?
Just the variable. I didn't want to use x also. W is just, you know, my parameter for R to the n, so to say. Yeah, you're right. Thanks for asking again, because last time I used x and y also for my tropical variables to live in R2. But here, just to distinguish the notation from variables over the Puiseux series and variables I wanted to use a different letter, so yeah. Okay. This theorem is it's actually not too bad to prove, at least if you believe that the field of pre-series is algebraically closed, because the difficult direction of the theorem is essentially equivalent to showing that the field of pre-series is algebraically closed. And the easy direction is really obvious, and I want to show you the easy direction. Proof easy direction. Because I believe that if you see this, and you see the easy direction, then you sort of buy it, right? That already helps. So let's do that. So let's assume we have a point x in our V of f intersected with a torus. And let's give this point x some names, right? X has coordinates, and all those coordinates are Puiseux series. So x1 is some Puiseux series, a1 t to the minus w1 plus, and so on. Up to xn. Xn is also a Puiseux series starting with an t to the minus wn plus, and so on. Okay. And why did I choose to label those with a minus here? Because now I want minus val, which I want to be the tropicalization, right? Should be wi. So I'm avoiding the signs when I move to the tropical world. Okay, what do we have to show? We have to show that this maximum here is attained twice at my concrete vector w that I get now from this point x, right? So let's write this down to show max minus val a alpha plus alpha times w attained at least twice. Because then this is actually a tropical zero, in the corner locus of the tropical polynomial, right? So let's show that. It's actually rather easy. What we do is we just plug our point into the polynomial f. What was the polynomial f? It's written here. Yeah, so this is sum over all alpha, a alpha, and then x to the alpha is, of course, x1 to the alpha 1, and so on. So x1 is a1 t to the minus w1. That comes to the alpha 1, and so on, times. And then xn is an t to the minus wn to the alpha n. Okay. And now let's understand the valuation of one of those terms, first of all. Not the whole sum, just one of the terms. What is the valuation? Yeah, what are we having? I mean, here we're getting a minus w1 to the alpha 1, right? And then we add those all up. And so we have minus w times alpha, right? But then we also have a contribution from this coefficient here, which, well, has some valuation. I don't know that yet, but I just write val of I alpha, minus w times alpha. So that's the valuation of one term, okay? Right, but now my x was out of my hypersurface, right? So f of x is actually 0. That vanishes, yeah? So here I wrote down a gigantic, ugly series, and I know this series has to be 0, yeah? So all the terrible terms that I wrote down have to cancel away and just disappear. In particular, the ones that have the lowest valuation, yeah? They need to cancel each other out. But that is only possible if there are multiple of those. Yeah? Cancellation can only happen if we have at least twice the terms that have the lowest exponent. So since this is 0, we can deduce val of I alpha minus w alpha has to be, the minimum. The minimum of this has to be attained at least twice, meaning for 2 terms, alpha at least, and then you just put a minus in front, and then this is precisely what I wanted to show. Yeah? So the easy direction is really just you put in points and you check what's happening to the valuation, and then you see that it has to be there. And I hope that this gives you a good intuition to believe that this is actually true. Okay, so with that, I want to go back to the purely tropical world, because my lecture series is more or less going to be purely in the tropics, so to say. Yeah? Yeah? So what's the confusion? Confusion about max and min? That's very normal. You have to accept this if you want to be in tropical geometry. Yeah.
So for instance, you wrote to show max, and then you show min.
Yeah, but I showed that the max of minus val A alpha plus alpha W is attained twice. And I showed that the min of val A alpha minus W alpha is attained twice. You just put a minus in front, and that works.
My confusion. Thanks.
Okay. You're welcome. Good. Okay. Yeah. This max and min confusion is totally normal. Yeah. I was serious. You have to accept it. It happens all the time. Yeah. Good. Okay. Right. So back to the purely tropical world. What we want to do in the tropical world, one thing I promised you in the preview and on the first day, is that I want to prove a formula for those numbers n-trop d0, right? And we know what those numbers are in the algebraic world. They count rational curves of degree d, satisfying 3d minus 1 point conditions, where the points are supposed to be in general position, right? But we don't really know, not fully yet at least, what this should be in the tropical world, right? We got some ideas from the first class. What did we learn? We have some ideas about what the degree of a tropical plane curve should be, right? Well, I guess one can have some ideas of what it could mean for a tropical plane curve to pass through points. That seems rather intuitive, right? But what about the genus? The genus is still something that is a little bit confusing. And that is one reason why in the tropical world it's particularly important to think of your tropical curves not as embedded objects, yeah, tropical curves in the plane, but to parameterize them by some abstract curves. And of course, you know, after the lectures of Drouf and Renzo, I think this is something that you will find totally natural, because what are we doing if we consider stable maps, or if we consider covers, or, you know, maps of curves into something else? It doesn't have to be covers of another curve, right? We take an abstract curve and we map it somewhere, right? And that's what we want to do in the tropical world also. What do we need to parameterize the pictures we've been looking at last time, right? Those tropical plane curves? Well, graphs, right? So very roughly, our tropical abstract curve is just a graph. We have to get some things right and make this more precise. And this is what I want to do now. So I want to introduce abstract curves. Then I want to introduce maps, putting the abstract curves into the plane so that we sort of get our plane tropical curves from the first lecture back, yeah, but now parameterized by graphs. And once we have that, we can go and really define what we want to count. That's the goal. Okay, so let's do that. So an abstract tropical curve is let me say, a connected graph. And then we also, something that is maybe not completely obvious, but that helps when we do parameterization, is to keep track of length, yeah? Because, so we saw already that weights play a role for our plane tropical curves. We have to pay attention to weights on the edges, right? And where do the weights come from? They somehow come from the length compared to the length of the image, yeah? So, you know, sorry, I should draw a picture to make this more precise. So imagine I have a very small abstract graph that I map to some picture in the plane. Now the picture in the plane almost looks the same, sorry, but that's how it is. So this is, you know, my balanced tropical curve. Maybe even just a 3-valent vertex would have been, no, it wouldn't. I wanted to talk about length, sorry. Now this is some point, and this is also some point, so I can measure the length of this interval, right? And I want to relate it to the length in the abstract graph, yeah? And then the weight should be the stretching factor that I need to go from one to the other. This is a way to somehow incorporate this very important weight data that we need for the embedded side into our definition, and for that, you can view that as one justification why it's a good idea to keep a metric for our abstract graphs, which are just, our tropical curves here. So it's a connected metric graph. with so-called ends. These are the unbounded edges. Ends. The ends are of length infinity. Yeah, and with a genus function. G from the set of vertices of my graph to n. And this genus function is there because this is something that Renzo also already told you. Renzo has drawn these degeneration pictures where you bubble off Riemann surfaces, yeah? And then you draw, yeah, just a dual graph. So you draw a vertex for each component and you draw an edge for each point, each node where two components meet. Yeah, for each node. Could also be self-node, of course. But then, since a component could still have higher genus if we're not completely degenerating, right? We need such a genus function to keep track of what's happening in the degeneration somehow. I have to tell you, however, I mean, my aim is to give you a formula for ND0 trop, so for rational tropical curves. So if you don't like that genus function a lot, just ignore it, because we'll only work with rational graphs in a second anyway, okay?
Does the metric graph not already come with the genus function? Or
It has its first Betti number, exactly. And yeah, very good question, because now I'm going to define what the genus of a abstract tropical curve is, and it's going to be the sum of what is still there in the graph and what is hidden at vertices. Yeah, and that is precisely the right thing to keep the genus from such a degeneration. That's, if you just draw the pictures that Renzo has drawn and draw the dual graph, you see that immediately. So the genus, genus is the first Betti number of the graph. You might also call it the genus of the graph, right? Plus the sum of, G of V with all vertices. Yeah, we call it marked if some of the ends are marked with some numbers. And then it's called stable if the genus 0 vertices are at least 3-valent. So I know some of you use degree instead of valency. In the tropical world, use of valency is very common, so let me stick to it. But of course, you can translate to degree or cubic, as you like. Okay, and then the combinatorial type. Combinatorial type is everything minus the metric. Yeah, so we forget about the length, but we keep all the rest. So let's discuss some examples. And let me actually do rational examples, because rational is the case I want to focus on. I want to count rational curves here. So let me assume I have 4 marked ends. This is a 3-valent graph right now. Ends are somehow marked, 1, 2, 3, 4. And then I need a length function on my bounded edges. I'm not writing down genus at the vertices now. If I don't write anything, it's a genus 0 vertex. And I want that to be the case because, as I said, I want rational curves. So the total genus should be 0. But I need length. The ends have length infinity. This could have a length, I don't know, maybe 2.5 or so, right? It could also have length 3, right? Then those two are 2 abstract tropical curves of the same combinatorial type. Because if I forget about the length, I just have the same graph, yeah, the same combinatorial, marked combinatorial thing. Have the same combinatorial type. Okay, and what are all combinatorial types of 4 marked genus 0 abstract tropical curves? all combinatorial types? Well, you need to be 3-valent, or higher valency is of course also possible, at least 3-valent, it said. If the picture looks like this, I have 3 possible ways to mark, right? I can have 1 with 2, or I can have 1 with 3, or I can have 1 with 4. Okay, let me just complete the remaining markings, 2, 4 here, 2, 3 here, and then these are all combinatorial types for this situation. Yes, please.
Also, edges can be marked or only ends?
The edges are not marked, no, it's the ends which we want to mark, that's right. And maybe not even all ends, but some ends. Yeah, I think it will make more sense as I move on, yeah? Okay, well, you know from Drew's and Renzo's lectures how important moduli spaces are if we want to count something, right? Admittedly, right now we're in the abstract world, so we're not at the parameterized tropical plane curves where we want to get, right? Nevertheless, the moduli space of those will be useful, will be interesting, and will be needed as we move on and discuss the moduli space that we really need somehow. So how do I want you to think about a moduli space of tropical curves? I want you to think of it as an abstract polyhedral complex. So it's not necessarily a fan. We will learn that in genus 0 it actually may be embedded as a fan in some big vector space, but let's not bother about this at the moment. So we'll discuss cones, and the cones will correspond to the combinatorial types. And I'll just tell you how to glue the cones. Yeah? And I don't care about any big vector space in which this might all live, because I just consider it as an abstract polyhedral complex. So cones that are glued, that's all. Yeah? And how are we going to glue cones, and what are the cones? So first statement, if you have a combinatorial type, for a combinatorial type that has B inner edges. When I say inner edges, I mean those guys, not the ends. The ends have length infinity anyway, but the inner edges. So for combinatorial type with B inner edges, I can take an R bigger 0 to the B. So an open orthant, yeah? And every point in this open orthant will correspond to a choice of metric on my combinatorial type. Yeah? So this orthant parameterizes all tropical curves of this combinatorial type that I chose, right? Something you might want to think about in one of the practical sessions, if you are 3-valent and have n ends, then you have precisely n minus 3 inner edges. So n minus 3 is the maximal number of inner edges such a graph can have. And so that means that's going to be the maximal dimension. My maximal dimensional cones are going to have dimension n minus 3. That's good. And then I glue orthants. I glue orthants by identifying the limit of a family of tropical curves with a vanishing edge. Yeah? That when I go to the boundary of this thing, right, then I'm setting one of the lengths at least to 0, so I'm shrinking one edge. The limit after shrinking an edge, or possibly several edges, after shrinking edges with just the curve without those edges. Okay. Yeah, and then I do this, and then I obtain an abstract polyhedral complex, and I call it M0n drop. Okay. So let me draw a picture. assume I have such a family of tropical curves. Let's add the markings, 1, 2, 3, 4 maybe. And I let L shrink to 0, yeah? And I want to identify the limit of this family of curves with the guy where this edge has just disappeared, yeah? And then I clue the orthon corresponding to this. Okay, for this particular case, the orthon is just a point, yeah? Anyway, I clue this orthon to the boundary that corresponds to shrinking this length for this orthon. This is the way how I clue. And this is the way how I obtain my M0n trop. So let's do an example. Yeah, I actually need more space for being able to do an example. Let's discuss M04 trop. This will be easy now because we already prepared, because we listed all the combinatorial types in M04 trop. Yeah? And now one is special because that one doesn't have any bounded edge. That's just a point, one such tropical curve, that's it. Yeah? What about the others? For any of the others, I get an open ray, right? Just an R bigger 0 for varying this length. And then when I shrink the length to 0, no matter which of those types I'm in, I will end up at the same guy at this point. So I should take my 3 rays and merge them at a vertex. This is what M04 trop is. Such a picture. And just to keep track of who parameterizes what, the point is this. This is like 1, 2, 3, 4, length L. Well, length L is something here, right? This is 1, 3, 2, 4, let's say. And this is 1, 4, 2, 3. Okay. Now you look at this, and I hope you all look at this and say, but wait, that's a tropical line, right? Why do we expect this? Why do we think it should be a tropical line? You know that from Renzo's talk, because he told you what M04 is, right? And he told you to think about M04 as a P1 with 3 special points, yeah? And so this tropical line, which is my M04 trop, knows where it wants to be embedded. This is what Dhruv told you. It knows that it wants to be embedded in P2, because if you embed a line into P2, you're missing 3 points, well, from the torus, right? You have 3 points in the toric boundary, 3 infinite points, right? And those 3 infinite points precisely correspond to my 3 rays. So the toric boundary restricted to my line embedded in P2 is precisely the modular boundary of M04 bar, right? And this is why this is so nice somehow. So we see already how things match really well together. Okay, right, I actually should erase a little more, because next we want to discuss how to embed those abstract guys into the plane in such a way that, as I promised, we recover those embedded tropical curves as images, yeah? Those embedded tropical curves that I hope we got all familiar to now. Okay, let me also erase that picture, even though it's so nice. Okay, so now we'll embed our abstract tropical curves into the plane. So let me define a tropical stable map. And it's a tuple consisting of an abstract tropical curve, gamma, some marked ends that I call x1 to xn, and a map H These are really hard to move. Such that gamma x1 up to xn. Sorry, I should also. I want to fix a special number of markings. I call it an n-marked tropical stable map. Little n marked. Here I have capital N. I want capital N to be bigger or equal to little n. So the little n ones will be special n's in some way. And I hope that this will help to convince Alessio also why it's useful to have special n's and to mark those special n's. Just to avoid having to work with too many group actions, I decide to mark all my n's and to always think of n's as being something marked. But nevertheless, I need to make this distinction. The small n ones are somehow special, and we'll see what is special. Okay, such that this is a marked abstract tropical curve. I should add abstract here, abstract tropical curve. And H is a map from gamma to R2. And very roughly, I just want you to think H maps gamma into R2 such that H of gamma looks like an embedded tropical plane curve, looks like what we've been studying the last times. Yeah? But to be a bit more precise, I'm going to tell you on each edge, each edge, H is affine linear with integer slope. What does that mean? I can identify my E with an interval from 0 to length of E. Yeah? And then H restricted to E will send T to a point R plus A plus T times V, where A is just a point, and V is an integer vector. Yeah, so my edge in the abstract graph is somewhere, yeah? And this edge gets mapped to, well, it starts somewhere, and then it also might end somewhere, depending on whether it's an end or not. And this is V. This is the direction. Yeah? Be careful, however, it's not the primitive direction. Yeah? It's the weighted primitive direction. That's precisely what I told you earlier about how the length in the image and the length in the abstract curve should be related. So think of V as the weighted primitive direction. We call it just direction. Weighted primitive, just to make it precise, but we only call it the direction. The direction. And then you realize, of course, that V is defined only up to sign, because it somehow mattered whether I parameterized this edge with the interval 0 to length or 0 to length, right? So V is only defined up to sign, V depending on the edge. Yeah, and now this is important when I want to talk about the balancing condition, because the balancing condition says for every vertex V, I sum over all edges adjacent to V. And then when I write V of E, I want you to think of the outward orientation, of course, right? And I want this to be 0. And that is our old balancing condition that we have for plane tropical curve. And we do not need weights here because they are already included in the directions. And now here's what is special about the first marked ends. I want the direction of the end, xi, to be 0 for all I from 1 up to n. I call those also the contracted ends. Yeah, the direction is 0 means they're all shrinked to just one point. Yeah? Those are contracted ends. So let me draw a picture. Sorry?
Is that n with capital
No, this is the little n. I want, so capital N is the total number of n's, and I have n, which is smaller in general, which are special. These are the contracted n's. Yeah? So here's an example. I always like to draw contracted n's as dashed lines to keep track of the fact that they are contracted. I need to give you some length. Let me just call all the length 1 to make my life simple. And I need to give those names, the markings x1 and x2. And then I have x3, x7, x4, x5, x6, and x8. Okay, so this is my abstract capital N marked tropical curve. And now I go and map it into the plane, R2. And the picture looks as follows. I want the direction of that guy outward pointing to be -1, 0. That should go diagonally up. Then this goes down. Now this guy is contracted. Now I want you to think of the balancing condition. What does it mean if an end is contracted in the 3-valence situation? Yeah, what does that mean? That means that this vector and this vector have to cancel each other out. Yeah, they have to be opposite to each other. And that means that guy is going to be just contracted to sort of like a point on an edge. Yeah, and in the image, you don't see that it is 2 edges. It looks like just one edge with a point on it. Yeah, and these are going to be our marked points. These are going to be the places where we can use an evaluation morphism from the moduli space of tropical stable maps to R2 to the n to evaluate where the marked points go. Yeah? Okay, I need to complete the picture. Yeah, so here's another marked point. Okay. Yeah, and of course I could be very precise and write down, I should maybe write down some coordinates for vertices. If this is 0, 0, then because this is length 1, this has to be 0, -1. This has to be 0, -2. This point is 1, -3. This point is 2, -4. And this is 3, -4. Yeah, so now you have an embedded tropical curve in the plane with sort of 2 special points, which are special because they come from wherever I had those contracted marked ends in my abstract tropical curve that parameterizes this thing. Okay, so I hope you like this picture, because from now on, I will never draw such a picture again, okay? I will only draw these things, and I will hope that you all always understand how I want to think. I want you to think of that as something being parameterized, yeah? I hope that this will always be obvious from the picture. Okay.
Explain what was the dashed line?
What is the dashed line? Yeah, it's just because it's just my way of drawing things. I like to draw those ends dashed because, so I should, right, thank you. I should say this, little n is 2 here, yeah? So the special ends, the contracted ends, I have 2 of those, and I like to draw those dashed, just to keep track of they are being contracted. Okay, now I'll define the degree of a tropical stable map, and that's going to be the multiset of directions of its ends, v of xi, but I don't include the zeros, so I say xi is not contracted. Okay, for my example that I've drawn here, what would be the degree? It would contain -1, 0 twice, and then 0, -1 twice, and then 1, 1 twice, okay? And now you look at that, or you look at that maybe, and you say, hey, wait, this is going to be dual to some triangle, some subdivision of the triangle of size 2, yeah? So when we were still in the embedded world, last lecture, we would call this thing here in the image, the h of gamma, we would call it a plane curve of degree d. Yeah, so D equal to a plane curve of degree 2, right? A conic, yeah? Okay, and yeah, so degree D would be sort of totally analogously, degree D would be D times minus 1, 0, D times 0, minus 1, and D times 1, 1, okay. Okay, good. So with that, I can define moduli spaces of tropical stable maps. So I fix a degree, delta, and I restrict to genus 0, as I said, let G be 0. And then I give you that space M0 trop of R2, comma delta. And of course, the notation is chosen in analogy to the usual stable map notation because it is totally analogous. And as I said, this is just all tropical stable maps. Of genus 0 and degree delta with n contracted ends. So the contracted ends are sort of our mark points, yeah? These are the ones where we want to evaluate. Okay. Now this is still just a SID. I promised you that my tropical moduli spaces will have some structure, namely the structure of an abstract polyhedral complex. How is that achieved? That is achieved by understanding the following equality. I claim that M0n of R2 delta can be identified with M0 capital N times R2. And the map that does this identification takes a tuple gamma xih and sends it to gamma xi, which is just an abstract tropical curve with capital N markings. And then it sends it to the evaluation of the first mark point, let's say. And I have to define what that is. I should have defined before, sorry about that. I want to define in general evaluation maps. EVI going from M0n crop R2 delta to R2 and sending this tuple gamma xih to just h of xi. Yeah? And I do that for I less than or equal to little n, because these are the contracted ends. So h of xi is a well-defined point in R2. Yeah, I can just ask somehow, where is this guy mapped to? Okay, that point. Yeah, that's what the evaluation map does. And now here that I picked the first one is just convention, just a choice. I need to choose one. Yeah, I choose one. Okay. Yeah, and I claim this is an identification. This is a bijection, actually. Why is that the case? Yeah, why is that the case? One thing to keep, let me actually just show it at this picture. Okay. So we have this data of our tropical stable map, right? And what we're doing in this map is we're just forgetting a lot. What are we actually forgetting? We keep this part, the abstract tropical curve, and then we keep the image of one point, this thing. Yeah? And that's all we keep from the information that is in this big picture. But I claim that these two things are sufficient for me to recover the full picture. Why is that actually true? Well, remember that I fixed the degree. So that means I sort of know the direction of those ends. I know that this guy has to go to minus 1, 0, and I know that this guy has to go to 1, 1, right? And then because we're in the rational case, by the balancing condition, I will be able to deduce all direction vectors for all edges that I have. Yeah? But then I have all the direction vectors. And then the lengths are there. The lengths are in the abstract graph. And with the direction vectors, I can also put length here. And then this is only a global shift that I still have, but I fixed this one point, so I know it. Yeah? Sorry, a question.
How do you know which of the directions from your degree go with which?
That I need to fix. That's a good point. I need to somehow remember what v of xi is. Yeah. So here I should have written this. So in my example, this was for x3, x4, x5, and so on. Yeah. Very good question. Yeah, Alessio, please.
When the graph is not trivalent,
Excuse me?
there is something else to say now. When the graph is not trivalent.
Yeah. The balancing condition still works, right? Nothing special. So if I know those three, I can deduce this guy.
Sure, but what if you know two of them?
What if I have two of them? Two of the higher valent vertices? It's always sufficient, yeah? If you want to make a formal proof of what I now said, you have to convince yourself that there will always be one vertex that has valency minus 1 ends. And then you do induction. And that you just do by counting. Yeah, good question. Thank you. Okay, so let's wrap this up again. What did we say? We said that keeping the information about the abstract graph and just one point of the image is sufficient. Why that? Because the abstract graph, together with the balancing condition and the degree, knows all the directions. But if I know all the directions and the length in the abstract picture, then I also know the length in the image. And that means I know the picture up to shift. But then I fix one point, and so I know the image, right? Okay, and that justifies why I have this identification. And that also justifies why it was important to me to talk about, oopsie, a trop missing here. If a trop is missing in any of my lectures, we just have to add it in, right? Because we'll be here purely on the tropical side. Sorry. Anyway, this also justifies why I insisted on first talking about this space so much, right? Because now you say that the space I actually care for, the space about stable, the space of tropical stable maps, this is just this guy times an R2. Yeah, so the abstract polyhedral complex structure is inherited from the M0n trop. Okay, now I have to pay attention to time. Okay, still some time left.
Real quick, this might just be semantics, but why would I even call this multiset a degree? Because I would expect degree to just be a number versus this weird object.
Yeah, yes. Yes. So as long as we're working in P2, I totally...
Can you repeat the question?
Oh, sorry, repeat the question. Yes, good. It's actually a very good question. The question is, why do I have something, such a funny thing like this multi-set as a degree? Because usually in the algebraic world, we're used to thinking of a degree as a number, right? And I agree with this notion of degree, as long as we are in P2, right? If we're talking about plane curves in P2, then of course they have this degree, which is just a number, right? But now we can also think about algebraic curves in other toric surfaces than P2, right? And well, the other toric surface I can describe by a polygon, which will describe an embedding of that toric surface into some projective space together with a hyperplane section, which is my algebraic curve. So in the toric world, I am used to thinking of a degree not as a number, but actually as a polygon. And now I'm even refining this, yeah, in the following sense, that I want to fix somehow the dual ends, yeah, and so it's more refined than the Newton polytope. For example, yesterday, when was the last time I talked? Whenever, Tuesday. We would call an object like this also a tropical curve of degree 2, because it's dual to this Newton subdivision, to the big triangle, right? It's not subdivided, but it's the big triangle, right? But now I don't want to do this anymore. I want to say degree D only if this guy comes subdivided as I want to, Yeah? That means in this tropical world, actually like in the log world, I'm not only fixing the toric surface in which I want to work, but I'm also fixing the contact orders with a toric boundary. And for the moment, I fix them all to be trivial. Yeah? Does that help?
Yeah.
Okay, great. Yeah, so we still have some time. I don't think I'm not sure we managed to actually define the number I promised you to define, and the zero trop. But, well, we'll define it tomorrow if not. But let's prepare it at least. Okay, so here's the first lemma. Okay, before going into details, actually roughly, what do I want to do, right? I want to fix 3D minus 1 points, since I want to count nd0 trop, right? So my little n should better be 3D minus 1, right? And then I want to take the evaluation map to R2 to the n, so the product of all evaluation maps. Let me call it EV. EV being EV1 times and so on times EVN, right? And then when you go and fix your favorite choice of 3D minus 1 points, then I want to count how many of my tropical stable maps actually meet this point, meaning I want to count inverse images, right? I want to determine the degree of the evaluation map tropically, okay? We all know that if we count inverse images, we have to be a bit careful, because sometimes we need to count with multiplicity. And of course, this is the case in the tropical world. So the next topic is somehow how to understand this multiplicity. And that's what this lemma does for us. So first EVI is linear on each stratum of my tropical moduli space. And if the number of marked points is the number of elements in my degree minus 1, so for example, 3D minus 1, if I am in the degree D world, yeah, which I want to be, of course, this product of all evaluation map, so it's a linear map, I can think of it as a matrix, and I claim it's a square matrix. Why is that? Well, it's just a dimension count. A 3-valent type. 3-valent, we know, is the biggest combinatorial type we can have. So that will have n plus number of elements in the degree. That's the total number of n's we have, capital N. N minus 3 bounded edges. But we have to add 2 to our dimension because of this 2, right? N minus 3. Capital N minus 3 is the dimension of this guy, plus 2. Yeah? Okay. So that is sort of the dimension I have in the biggest cone on this side. And on the other side, I have 2n, which is 2 times number of delta minus 1. And so this is honestly an equality, and so I really have a square matrix. And then I define the multiplicity of gamma, xi, and h to be the absolute value of the determinant of this matrix. Let me check the time. Yeah, no, we are running really out of time. But maybe I can do one final example. Let you see this working. So let's imagine we're counting lines through 2 points, tropical lines through 2 points, fit into this moduli space setting right now. So a line comes with 2 contracted ends, like this here, right? x1 and x2, and this is x3, x4, x5, and here are some length, L1 and L2. Yeah. This is just one stratum in the combinatorial type right now. There are more, of course, but let me restrict to this. And I want to view this as an element in M0 6 times R2. And then the first evaluation is projection to R2, because this is the coordinate. This is the one point we kept in the information from all the image, right? Just that one point. Okay. And what is the second evaluation? Let me actually give this the coordinates. Let me say this has coordinates x, y in R2, okay, for my special choice here. And then the evaluation 2 of gamma xih, I can write it as, well, I start at xy, right? This is xy here. I start here. I go L1 in this direction, which is 1, 0, and I go L2 down. Yeah, so it's a relative evaluation. So it's xy plus L1, 1, 0, plus L2, 0, minus 1. So what is the matrix? I have 4 coordinates of my cone, x, y, and L1, L2. And I'm evaluating 2 points. The first point is just here the identity matrix on x, y, because it is just the projection to x and y. And the second has x, y, but then plus 1, 0 times L1 plus 0 minus 1 times L2. Okay, good. So we stare at this matrix, and we all see immediately that its absolute value of the determinant of this thing is 1. And so we are happy because it says that counting a line through 2 points, a tropical line through 2 points, counts as 1 with this definition of multiplicity, which is very good, because what else should it be, right? Okay, now I think I went a little bit over time, so apologies for that. But yeah, since coffee is long, maybe there's still enough time for maybe some short questions that you might have. No, everyone tired and out of steam at this point. Okay, good. Let's have coffee then.